Let us start this lecture with a thought process from great Saint Swami Vivekananda, who says one may gain political and social independence, but if one is a slave to his passion and desires, one cannot feel the pure joy of real freedom. This is a very interesting and apt statement for all of us, as most of us want to experience the real freedom, and which is the main objective of human life as enshrined in our scriptures, and also most of us feel that way. And this is a very good recipe, and for which we must work to experience real freedom. Let us learn in the last lecture what we learned. We initiated discussion on combustion of the composite propellant. During this combustion process, we looked at various kinds of flame. If you recall that we looked at basically three kinds of flame are formed as per the model of BDP, that is Beckstead, Durr and Price model. And these three flames in a composite propellant are monopropellant premix flame, primary diffusion flame and the final diffusion flame. And if you look at they have considered a very simple composite propellants composition, that is only the ammonium perchlorate and the binder or a polymer STP maybe. And we also learned that at low pressure the combustion is controlled by the premix flame, and whereas at high pressure the combustion process will be controlled by the diffusion flame. Keep in mind that the thickness of the flame decreases with increase in the chamber pressure. And after that also we learned how to determine the burning rate or the regression rate of a propellant, and we learned that there are three methods which have been devised to measure the burning rate of a solid propellant. And these methods are the Strand or the Crawford burner, which is quite standard, is being used routinely, and the other two methods are being sparingly used. One is the small scale evaluation motor and full scale evaluation motor, but keep in mind that full scale model will give you the right result as the actual condition will be prevailed in the combustors. And scaling is also very critical and also difficult to achieve in wherever combustion is involved. So, therefore, it is not being used very much. However, it is easier to use as compared to full scale burner. Besides this, we have also discussed about a very widely used relationship between the burning velocity and chamber pressure, which is known as the Helis law or the Saint and Robert law, and that is being used very much. And keep in mind that that is a semi empirical relationship that we had derived, and that is valid for both the double base propellant and single base propellant. And that law, let us recall that we had derived a semi empirical relationship for burning rate, which is like this: R dot is equal to A P C N. And if you look at this, N is the pressure index and A is can be expressed as A divided by T I minus T P. Look at this, A P is basically a constant and T I is the self ignition temperature and T P is the propellant temperature. And keep in mind that A depends on the composition of the propellant, as the self ignition temperature will be different for different composition of the propellant, and T P is the propellant temperature which is being controlled by the ambient temperature. So, therefore, A is small a is not really a constant, it will be influenced by the composition of the propellant and also the way the propellant grain is being designed and fabricated. And keep in mind that constant or the A is independent of chamber pressure. Now, let us look at the effect of the propellant temperature on the burning rate or the regression rate. And if we will consider an example like R dot is basically 176 divided by 415 minus T P, and this is for a particular composition of the propellant, and this is nothing but your T I, and this is basically constant A. And if we will vary this T P, that is propellant temperature, and also the vary chamber pressure, we can get a data, and we have plotted this variation of burning rate with the chamber pressure, 3 propellant temperature. If you look at, this is corresponding to T P is equal to 240 K, you can see that the burning rate increases with the chamber pressure, and this is of course, as the chamber pressure increases, and this is increasing in a nonlinear manner. And of course, when the temperature increase when the propellant temperature increase to T P is 280 Kelvin, there is a increase in the burning rate, and the increase in burning rate is more predominant at the high chamber pressure, and this curve corresponds to T P is equal to 320 Kelvin, and of course, there is a increase in burning rate with increase in propellant temperature for a particular chamber pressure. If I consider this is the one, this is increase, right, for a particular chamber pressure of 16 megapascal, there is a increase. This increase in burning rate due to the change in the propellant temperature for a particular chamber pressure is becoming higher as when we increase the chamber pressure. And keep in mind that this is can be really important one, and when this T P is tending towards the T I, that means propellant temperature is closer to the self ignition temperature, then the burning rate will be increasing at a faster rate, particularly at higher chamber pressure. Then it may lead to explosion. It may lead to explosion. That means, the burning rate becomes infinity, and particularly at high chamber pressure. So, therefore, one has to be very careful while designing a solid propellant by controlling its chamber pressure. We will be looking at how this burning rate is sensitive to the propellant temperature. Let us now look at little further about the variation of burning rate with the chamber pressure and also propellant temperature, considering some of the typical solid propellants which is being shown here in this graph, and keep in mind that we will be using this Saint and Robert law, and which is being plotted over in this figure, and this is the burning rate which is given in inch per second, and the chamber pressure in psi. Psi is pounds per square inch. You can see that here the burning, it is being plotted in a log scale, and let us consider the double base propellant. This is the double base propellant, and it is increasing with the chamber pressure, but when it beyond this 400 psi, it is remaining almost constant, indicating that the pressure index will be 0, and this also we call plateau burning. And let us now consider the composite ammonium nitrate propellant, which is shown here, that the burning rate increases with the chamber pressure at 40 degree Fahrenheit, and keep in mind this looks to be linear or a straight line, and the slope will be having certain values you can find out, but whereas having some finite values. And as the temperature increases to 60 degree, there is a slope remains almost similar, but increase in the burning rate, and so also with further increase of propellant temperature to 140 degree Celsius, there is similar behavior, but with increase in burning rate. And of course, if you look at the composite ammonium percolate correspond to this one, this is again the similar behavior. Keep in mind that this slope is smaller than the ammonium nitrate propellant, but in this case the range of burning rate is higher. If you can consider this is something around maybe 0.24 inch per second, it goes to the maximum maybe around 0.4 inch per second, whereas composite ammonium nitrate propellant is very low. It is something around 0.03 to the maybe 0.125 inch per second, and but its slope is higher and this slope is smaller, but positive. And keep in mind that if we will have this JPN type double base propellant, you will find the similar behavior, only difference is that its slope is much higher as compared to ammonium nitrate propellant, but the behavior is same with the change in the propellant temperature. And another things which I could have discussed is that this line, you can see dashed line corresponding 68 degree, and this belongs to this high energy XLDB composite propellant, is basically RDX, that is research development explosive, being added to this propellant. There is a increase of the burning rate. It goes from maybe 0.175 to the something around 0.8 inch per second, and slope is quite high. If you consider this, slope is quite high as compared to composite ammonium percolate. And there is another high burn rate propellant which is shown here, corresponding to 68 degree Fahrenheit, that it is also higher slope and high range of the burning rate as compared to even high energy XLDB composite propellants. Of course, the slope is little lower as compared to the this XLDB composite propellant, but range is something 1 maybe 1 to beyond this 2 or 2.1 0.1 kind of inch per second. So, let us summarize what we can learn from this discussion on the burning rate variation with the chamber pressure for a 3 or range of propellant temperature. So, if you look at, we have seen that the regression rate or burning rate increases with chamber pressure, and the burning rate increases with propellant temperature, and the regression rate varies from 0.1 to 75 mm per second, which is not shown here, but this 2 inch means it will be basically something around 50 mm per second, but however, we will see in the next slide that people have achieved around 75 mm per second. However, the common burning rate range is something around 6 to 13 mm per second. That means, if you look at this range, 13 will be around this, and maybe 6 is around this range is a lot of kind of things is there. And the pressure index N is lower for double base as compared to composite propellant. Keep in mind, it is not shown here. The JPN is a mixture of these propellants, but you can see this slope in the double base propellant is very low N values, and therefore, it may be subjected to unstable, or maybe it will extinguish at a certain pressure, low pressure. Addition of nitramine RDX propellant can enhance the burning rate and pressure index that we have seen. It is enhanced, the burning rate has been enhanced quite a bit, and so also the pressure index. Question arises whether we can have a propellant with negative pressure index. So, we will see that. So, we are using this Sent and Robert law for this burning rate relationship with the chamber pressure. So, if you will use that, and some of the data we can see, I mean like if you plot this ln r with ln pc, this is corresponding to basically APCN, but however, in this case the n is positive. In this case, n is greater than is basically 0, is a positive value, whereas n is equal to 0, and this is the plateau burning. If you consider that plateau burning is really more sought after, because of fact that burning rate is not changing with respect to the chamber pressure. In other words, the thrust will not be changing with respect to change in the chamber pressure. That is a very good thing, but however, this is also problematic to some extent, because of fact that it may lead to the instability and may extinguish at certain time, and most of the double base propellant will be experiencing this, and this can be the pressure index N can be modified by varying the rate of chemical reaction in the phase zone, what we have seen in the case of double base propellant. And there are several ways of doing that. You can add some chemicals, so that the chemical reaction rate will not be varying on the burning surface. The heat release in the phase zone will not be changed in this due to the constant burning rate with respect to chamber pressure. And this can be achieved by adding several chemicals into that. For example, a small amount of lead compound to the double base propellant can alter the reaction rate such that the burning rate is independent of chamber pressure, and this pressure N becomes 0 or otherwise it is tending towards 0, and this results in the plateau burning, and that means N is equal to 0. And keep in mind that when N is negative, right, then you can have a mesa burning. This is basically normal burning, we call it normal burning, and this is because n is the slope of this is negative. So, therefore, n will be having negative, and this is known as the Mesha burning. This is known as Mesha burning because n is less than 0 or the negative. And this propellant which exhibit negative value of index is known as the Mesha burning, as I told, which is useful for restartable motor, rocket motors or the gas generator. So, that what will happen, that when you will the pressure will be decrease, right, the lower pressure you will have to operate, then the burning rate is very high. So, that it will not really lead to any instabilities or extinction of the combustion. So, therefore, it is very useful for that, and keep in mind that this plateau burning and Mesha burning are found mostly in the double base propellant, but however, in some composite propellant you can also find the plateau burning. And keep in mind that this semi empirical relationship what being used profusely was basically derived for internal ballistic rocket motors, and of course, the more natural and more general form of this expression for the regression rate will be R dot is equal to A P C power to the n plus b, and this b and a is basically dependent on the temperature, propellant temperature. It is independent of the chamber pressure. However, it is really not being used very much, but it is the more general, and maybe one can. The another things which is being used is known as Murray laws, meant for high chamber pressure, and which was developed particularly for artillery gun is R dot is equal to A P C plus B. Keep in mind that n is equal to basically 1. So, that it became A P C, that means it is only linearly going with the chamber pressure, and this is because of fact that this is at very high pressure, and then the changes is not really much will be occurring. So, therefore, we have seen now this kind of various kinds of burning, and then we look at in the next lecture about little bit more data on this burning rate and see that what we can. Thank you very much.